Hello AP Mechanics C student, welcome back to our new video. In this video, we are going to solve 2017 set 1, question number 1. An Atwood machine consists of two blocks connected by light string that passes over frictionless pulley of negligible mass, as shown in the figure above. So as we can see here, we have two masses, M1 and M2, hung by two strings that is connected to a pulley. The masses of the two blocks M1 and M2 can be varied. M2 is always greater than M1. And we mean by that the acceleration here will be acting downward for the M2, and for M1 it's acting upward since M2 is heavier than M1. Now on the dots below, which represent the blocks, draw and label the forces, not components, that act on the blocks. Each force must be represented by a distance arrow, starting on and pointing away from the appropriate dot. The relative length of the arrow should show the relative magnitude of the forces. So here they are giving me instructions to make or to construct the free body diagram. We need to represent all the forces, we need to label them, and we should take care about the relative length. And this happened whenever we have in the background of the free body diagram a skeleton or gridded shape. Now to do so, we need first to determine the forces acting on each body. So let's start by determining the forces acting on M1. Here on M1, we have two forces acting on it. The force of gravity, which is acting downward, and the tension force, which is acting upward. Now we know that since the pulley is massless pulley, and which means it has a negligible mass, then the two tension on M1 and M2 are equal, and this should be reflected on the sketch. Now let's start by drawing the tension force. I will draw the tension force here to be exactly equal to two grids. So this is tension 1. And the force of gravity, since the object or block M1 is accelerating upward, then the force of gravity must be less than the Ft. And I will draw it by only one grid. So this is the force of gravity, 1. Now here, since the pulley is, again, it's a massless pulley, then the two tensions on the string must be equal. So make sure to draw the length of the second tension equal to the first one. Now, since the second mass is heavier than the first mass, then the force of gravity acting on this mass must be greater than in the first case, the one in the first case. However, we need also to show that this force of gravity must be greater than the tension force in order to accelerate downward. So the force of gravity should be drawn in this way. Now, using the forces in your diagrams above, write the equation applying Newton's second law to each block independently, which means, and use these two equations to derive the magnitude of acceleration of the block, and we need to show that at the end of our work, the acceleration is given by this equation, m2 minus m1 over m1 plus m2 times g. So let's start by considering block m1, and whenever the acceleration is involved, we need to use one of the big laws to find its expression, and the big law here is the Newton's second law. So we need to refer back to this law by saying or writing, applying Newton's second law on block 1. So Newton's second law said that F net is equal to ma. Now, how many forces acting according to the free body diagram we have on block M1? Two forces, F2, Ft, and Fg1. So Ft plus Fg1 equals to ma. Now here we have the factorial equation. We need to apply the projection in order to get the acceleration along the y-axis or the vertical axis. So let's project along the vertical axis. Now back again to the sketch, we know that the acceleration is acting here upward. So whenever this happened, take the positive sense to be upward. So this is applicable for block 1, which means the tension force is acting up, the tension force is positive, and for the force of gravity, which is acting downward opposite to the positive sense, we should use the minus sign to represent it in the projection step. So Ft minus Fg is equal Ma. Now we know that the Fg is equal mg. Now we move mg to the other hand side. We change the sign from from minus to plus, and we will get the first expression for the tension of the string on block M1. Now let me pay your attention to something very important here. I didn't specify which mass we are dealing with. I wrote in general M, and can be considered to be wrong. We need to specify the mass that we are dealing with, and the mass here actually is capital M1. So let me mention this. So M1 here, M1 here, M1 everywhere. Now, we apply the Newton's second law on the first block. However, we need to do that for each one of them. So let's apply Newton's second law on block M2. Again, we have the F net is equal MA. Now Ft plus Fg equals MA, since the same forces or the same type of forces are acting on block M2. Now project along the vertical axis, and we will get that the following. Now here, in this case, the acceleration is acting downward because block M2 is accelerating downward, which means the positive sense must be taken to be within the direction of acceleration. Now, any force is pointing down, it should be treated as a positive with a positive sign. And for any force that opposing this direction should carry a negative sign. So we simply add plus and minus accordingly for Ft and Fg. So we write that the Fg2 is a positive and the tension is negative. Now again, let me here specify which block we are dealing with. Here we are dealing with M2, capital M2. So M2G minus Ft is equal M2A. Let's move the M2G to the other hand side. It becomes negative, and we'll get that the minus Ft is equal M2A minus M2G. Now let's multiply both sides by minus 1 in order to change the sign of Ft from plus to minus, and we will get that Ft is equal minus M2A plus M2G. Reorganize this equation and you will get the equation for Ft. And this is the second equation that represents the tension on block M2. Now we know that the tension on block M2 is equal to the tension on block M1. So let me write here that the two tensions are equal. So I can use now the corresponding equation to complete my derivation for the acceleration of the system. M1A plus M1G equals M2G minus M2A. Now we just need to move the similar term next to each other, M1A with M2A, and M1G must be moved to the side that M2G belong to. So M1A, let's move the minus M2A to the other hand side, it becomes a plus, equals M2G. By moving M1G, it becomes minus M1G. Now taking M2 as a common factor here, and sorry, we're gonna take G as a common factor here, and A as a common factor there. Now A multiplied by M1 plus M2, and here M2 minus M1 multiplied by G. Now dividing both sides over M1 plus M2, this and this cancelled out, and finally we will have the expression of acceleration of the system, and it should be identical to the one that they asked me to show. The magnitude of acceleration A was measured for different values M1, M2, and the data are shown below. So here in this data, we repeated the experiment for many trials. So this is trial 1, this is trial 2, this is trial 3, 4, and 5. Now, for each trial, we have measured the acceleration that's corresponding to these masses, and the acceleration in the first trial, and the second, third, and so on, are given and provided in the table. Indicate below which quantities should be graphed to yield a straight line whose slope could be used to calculate the numerical value of the acceleration due to the gravity. So our target is to find the acceleration due to the gravity by utilizing the slope from a straight line that the graph would show. Whenever I said straight line, I should to recognize that the equation of the straight line must be written as y is equal to mx plus b. Now, in the previous step, we have calculated the acceleration of the system, and the acceleration of this system is given by m2 minus m1 over m2 plus m1 multiplied by g. Now, by setting g in front, we can come up with this equation. Let me change it. I just need to reorder my equations to make it aligned with the linear one. So g m1 plus or minus here m2 minus m1 over m1 plus m2 times g. Okay, so now let's compare the two results. Why did I bring the g in front? Because we're gonna utilize the slope, which is represent the g, to calculate its value. And according to the order provided by the general form of a linear equation, the m should be written first. Now, let's compare the general form with our corresponding equation. Now, y, or the vertical axis, represent the acceleration. The slope, according to the question, represent the acceleration due to the gravity. And the x, which is multiplied by the slope, represent the horizontal axis, which is exactly equal to the m2 minus m1, m1 plus m2, because this quantity or the fractional mass here is multiplied by g. Finally, what about b? Now we know that b, it can be positive, negative, or even zero. Since we don't have any number here added or subtracted from our formula, then we can assume that b is equal to 0. So no zero here. From this comparison, we can say that along the y-axis or the vertical axis, we must plot the acceleration of the system. And along x-axis, we must plot m2 minus m1 over m2 or m1 plus m2. No need to write this in our answer sheet. So we just need to show the label of the vertical axis and the name along the y-axis, or the quantity along the horizontal axis. Now, use the remaining rows in the table above as needed to record any quantities that you indicated that are not given. Now, the quantity that is not given here, according to the constructed equation, A is equal G m2 minus m1, m1 plus m2, is actually this quantity. Now, whenever we want to plot, we will need A and the fractional mass to get the slope. Um, Although they gave me or provided me with the two rows, however, I will need only one quantity here and no need to fill the second row. We just need to fill the first row. Now we write m2 minus m1 over m1 plus m2. Remember that whenever you want to present a new quantity in any table, you need to write this quantity along with the unit. However, here the fractional mass is unitless, and let me prove that. M2 has a dimension or unit of kilogram. M1 also is in kilogram, and in the denominator, it purely consists of kilograms. So if you subtract kilogram from kilogram, let's say 5 kilogram minus 4 kilogram, the answer will be 1 kilogram. So also the unit will be kilogram. And also after the addition, the net unit will be kilogram again. And kilogram cancelled with the kilogram, and you will end up with unitless quantity. So no need to show any unit for this fractional mass or in this row. Now we just need to apply simple calculation for this fraction. So m2 minus m1, m2 is given by 2, m1 is given by 1, over 2 plus 1 or 1 plus 2. And the answer will be 1 over 3, and we know that 1 over 3 is equal to 0.33. Now we repeat the same calculation for the other trials, and we will get the following values: 0.2, 0.41, 0.14, 0.17. Plot the data points for the quantities indicated in part C on the graph below. Clearly scale and label all axes, including units, if appropriate. If you have a unit, you need to plot it. If you don't have a unit for the quantity, no need to write it as a label. Draw a straight line, it must be straight, that best represent the data. So we start by adding our axes and labels. So this is the x-axis and this is the y-axis, or in other words, this is the horizontal and this is the vertical. In the previous question, we said that along the vertical we have the acceleration, along the horizontal we have the fractional mass. So m2 minus m1 over m1 plus m2. And for the labeling along y-axis, we have a meter per second squared. Now let's start by scaling our graph. Let's add the scale, which means we need to know what will be the step for each grid. Now, from the range of the numbers, you can come up with the appropriate scale. So, for example, here, our values for the horizontal axis are start from 0 and up to the maximum on, which is 0.4. So, which means that we can split our horizontal axis into grids with the step of 0.1. So 0 here, 0.1, 0.2, 0.3, 0.4, and 0.5. Now for the vertical axis, now as we can see here, the values range are from 3.02, or sorry, let me see the values. The minimum value is 1.15, so we can say that the minimum is 1 and the maximum value is 4, so we can split our grid with the steps of 1. So 1, 2, 3, 4, and 5. Now we can use this scale to determine the data or the point from the table. Now remember that this graph represents the acceleration and the fractional mass. So our data should be extracted from the acceleration line or row and the fractional mass row. So this is along the vertical, this is along the horizontal. So the first point is 0.33, 3.02. Let's go back here. 0.33 is actually located somewhere here because this is 0.3. So each small grid represents a step of 0.02 and 0.03, 33, it should be in between these two lines. So let me add a mark here, small mark for the 0.33. Now, the acceleration corresponding to this fractional mass is a 3.02. And that's 3.02 is somewhere here. So we use this dot to represent our data or the location of our point. Now we repeat the same thing for the remaining points. Here we have 0.2, 1.82. So actually 0.2 is here, 1.82 it's somewhere here. The third point is 0.41, 4.21, and 0.41 it's somewhere here, 4.21. This is the point. Now 0.14 with 1.15, 0.14, so 1, 4. So this is 0.1, 0.12, 0.14, 14, okay, and 1.15. So 1.15 it's somewhere here. And we will have the last point, which is 0.17 and 1.71. And 0.17, so 17, 0.12, 0.14, 0.16, and 0.18. So here we have 0.17 with 1.7 and 1.7, 1.2, 1.4, 1.6, and 1.7 should be located here. So the point is here. These are my data points for this experiment. Let me double check. Okay, so back again. Here we have okay, so let me double check this point. I need to double check this data. Now here we have 0.1, 0.2, 0.4, so 14, 0.14. At 0.14, the point, the y-axis or along the y-axis, the point should carry this location 1.15. Now here, this is not point 1.15. So let me just correct the location of this point. Now 1.15 this is 1.2. So 1.15 is between 1.2 and 1. So actually the correct location of the point will be exactly here. Now I have my points located correctly in the graph. Now let's draw the best fit line. For the best fit line, we will draw a straight line that passes through most of the points, or at least at equal distance from the points. So we may draw it in this way. Okay, so let me correct the location of this here. Okay, so it seems like my points are at equal distance and my line is passing through the points. Now you should choose your line in a smart way such that, for example, it passes through the corners of the grids. So you can collect the data or the points to calculate the slope in easy way. Now, for example, this point has a location to be 0.42 and along the y-axis is 4.2 meter per second squared. And for the second point, which is B, let's call it this one is B. Now the coordinate of this point is 0.14 and along the x-axis it will be 1.2 meter per second squared. Okay, so now let's use this point to calculate the slope because here using your straight line determine an experimental value for G. So we know that the G represent the slope according to the previous question. And to find the slope, we need to find the rise over run. For that, we need the data. Now avoid to take your points from the dots that you constructed from the table. You need to take your points from the best fit line. This is why I have located these 2 points along the best fit line and I extracted them and wrote their coordinates for each one of them here as A and B. So I didn't take this point, this point, this, or this, or this. I need points exactly from my line. This is the aim of the line. So we can write 42 minus 1.2. So delta y over delta x here. The data here are represent the y-axis or the point along y-axis and the point along x-axis here. So 0.42 minus 0.14. Now let's use the calculator to evaluate the acceleration due to the gravity. So 4.2 minus 1.2 over 0.42 minus 0.14. And the answer is 10.71. So this experiment, it leads to have a value for G, which is slightly different than the theoretical one, which is given by 9.81 meter per second. The error is accepted, and this value also is accepted. Now, the experiment is now repeated with a modification. So this is the modified Atwood machine. And the Atwood machine now is set up so that the block of mass M1 is on a smooth horizontal table and the block M2 is hanging over the side of the table. So as we can see here, we use the two masses, the same two masses as the experiment one, but this time M1 is placed on a horizontal surface, smooth surface. For the same values of M1 and M2 is the magnitude of the tension in the string when the blocks are moving higher, lower, or equal to the magnitude of the tension in the string when the blocks are moving in the first experiment. Okay, what will determine the value of the tension here is the acceleration of the system. So let's find out what will happen to the acceleration of the system after this modification. Now, to do that, we can restudy the acceleration of the system by mentioning the forces acting on the system. So we have the force of gravity here and the normal push. In addition to these two forces, we have the tension force acting to the right. Now here we have only two forces, the same as the first experiment. Now, since M2 is the one that we hung, then the acceleration will be acting down here and this block will move to the right or accelerate to the right. Now let's apply Newton's second law quickly on M1. So along M1, we have only one force causes the acceleration, which is in this case, the Ft. So we just need to write Ft equals m times a. And which m particularly, this is M1. And on the other hand side, for M2, we still have two forces, so we can write that the Fg is positive since it's pointing with the direction of acceleration, the Ft is negative, and it's equal to M2a. Now back again, we can rearrange this equation, and for sure we will get that the Ft is equal M2G minus M2A. Now, again, the pulley is a massless pulley, which means we can equate Ft here from Ft there with Ft there, and we'll get that the M1A equals M2G minus M2A. Now let's move the similar term next to each other. So M1A plus M2A is equal to M2G. Let's take the A as a common factor. Divide both sides over M1 plus M2 and we'll get this acceleration. Now this acceleration is the acceleration of the system when we place M1 on a horizontal surface. Now notice that in the numerator, we don't have difference. We have a purely M2 without any uh, additional part. Let's compare it with the previous acceleration in the first experiment. The first experiment, we found that the acceleration M2 minus M1. So M2 will be reduced by M1. However, in the second experiment, the MU, uh, the M2, sorry, is purely affecting the acceleration. So what happened here? Let's compare the two numerator because the other factors are remain the same. The M2 minus M1 is less than the M2, which means, in other words, the numerator now is higher, which means the acceleration is higher. So in the second experiment here, the acceleration is bigger than the one in the first experiment. So from this result, we can say that this part in the equation will be higher, which means that we will have the net of this difference will be less and the tension will be lower. So we can say that the tension will be lower. And how we can justify this? We can justify by saying that the acceleration of the system increases from A equals M2 minus M1 over M2 plus M1 times G to acceleration equals M2 over M1 plus M2 times G. But M2G remain the same, which means Ft in the string decreases. Now the value determined for the acceleration due to the gravity g is lower than the first experiment. Given one physical factor that could account for this lower value and explain how this factor affected the experiment. Actually here, although we have the smooth horizontal surface, but since we have witnesses in a different value or less value of the acceleration for the gravity, in comparison with the first experiment, then we may say that one of the sources or possible sources, and here we are speaking about um, experimental approach, or let's say we perform this in a real lab. So one of the possible sources for this difference is the existence or the presence of the friction. Now we can say that the friction is the reason. In the presence of friction, acceleration would decrease, then the slope of the line decreases. This will affect the value of G calculated in experiments. Thank you for watching today. See you in a new video soon.